Okay. Of this function, f of x equal to the square root of x minus 3 plus 5. Okay. In the first place, the square root of x minus 3 has to be greater than or equal to 0 because there's no number that you can square and get a negative number. Okay. You square a negative number, it's going to be positive. Square a positive number, it's going to be positive. Of course, they're imaginary numbers and they can be squared to give you a negative. But we're talking about the domain over the real numbers, and that's kind of implicit, at least in this course. Okay, so this has to be greater than or equal to 0. Now the question is, can it take any value at all that's greater than or equal to 0? Well, x minus 3 can take any value at all because it's a linear function. This graph would be a straight line, y-intercept -3, slope 1. It goes on forever in both directions. So it can take any value. The y value could be any number at all. But the square root only works if x minus 3 itself is greater than or equal to 0. Now, x minus 3 greater than or equal to 0 looks a lot like this must be greater than or equal to 0, but the two are not related. Okay, so my point here now, square root of x minus 3 only works if x minus 3 is greater than or equal to 0 because you can't take the square root of a negative. Okay? So it means that x has to be greater than or equal to 3. Now, any number greater than or equal to 3 gives you a value of x minus 3 that's greater than or equal to 0, so you can take its square root. So any x greater than or equal to 3 works. And there's no other restriction on the domain. You can take the square root of x minus 3, as long as x is greater than or equal to 3, you're going to get a result from the square root, a real number, and you can add 5 to it. Okay, so we can say the domain is the interval to infinity. Now the range, x minus 3 has to be greater than or equal to 0. So when we add it to 5, the result has to be greater than or equal to 5. Since x minus 3 can take the number, can take value 0 and any number greater than 0. When we add 5 to it, say that the range is infinity. Prove that more rigorously. We could say, okay, if y equals square root of x minus 3 plus 5, we can solve this for x. Okay, if we let's say we subtract 5, we get y minus 5 square root of x minus 3. So that y minus 5 quantity squared equals x minus 3. So that y squared minus 10y plus 25 equals x minus 3. This tells us then that x, if we add 3 to both sides, equals y squared minus 10y plus 28. Okay, well, what's the minimum possible value of y squared minus 10y plus 28? This gets us into the graph of this function. So this is quadratic. X at negative b over 2a equals 5. This means that the values of this function parabola would open upward. Now, talking about a parabola because we know how to graph quadratic functions. Okay, if we plot, now this might seem a little weird, we're used to plotting y versus x, but this is our function right now that we want to analyze. So let's just label our axes y squared minus 10y plus 28. From the properties of quadratic functions, we know that the vertex occurs equals 5. So here would be the line of y equals 5. This is the axis of symmetry. If we plug 5 in here, we get 25 minus 50 plus 28. And 25 and 28 is 53, so we get y equals 3. This means that the vertex of this parabola would occur at this point. And the y-intercept would be at 28. Well, let's not worry too much about that. We see that graphing this versus the value of y, this expression versus the value of y, our graph is going to be a parabola with vertex at 5, 3. That is, the value of this thing is equal to 3 here, when y equals 5. And this agrees with what we said about the domain. Okay. Domain is pre-infinity, and that corresponds to all the values from here on up. Okay, now remember, we solve for x. So this is the value of x versus y. There would say x equals this, which equals 3. So x has to be greater than or equal to 3. That's a little bit challenging. But of course, it also allows us to review some properties of quadratic functions. So take this example for what it's worth. Just to flesh it out a little bit, if we have minus 12x plus 16 by the quadratic formula, y equals 0 if x equals 12 plus or minus the square root of negative 12 squared minus 4 times 1 times 16. Minus the square root of, there's 144, and there's minus 64. Be 12 plus or minus the square root of 80 over 2, which is 6 plus or minus the square root of 80 is the square root of 16 times the square root of 5, and the square root of 16 is 4. So that would be 4 square root of 5 over 2 equals 6 plus or minus 2 square root of 5. square root of 5 is approximately 2.23, I think, or something like that. And 2 times that would be, I'll just say 2.2, but I'm still going to say 2 times that is 4.5. And that would be 10 for the plus or 1.5. Okay, so if we want to do graph of this function, well, the vertex occurs at 6 because 6 is halfway between 6 plus 2 square root of 5 and 6 minus 2 square root of 5. Now I've got a little bit of a bad approximation here. Okay, this is 2.25, not 2.23. Multiply that's 4.23. It'd be 10.5. $1.5 to do it accurately. So now we have the idea that our axis of symmetry is x equals 6, and we move 2 square root of 5, which is roughly 4.5 units to the right, and we get x equals 10.5. We move a little bit to the left, 4.5 units, and I'm not maintaining my symmetry very well, but this line is x equals negative, x equals 1.5 approximately. So let's move this line over just a little bit more. Okay. Our x-intercepts are the x values that make y 0. So y equals 0 if, I can say if and only if, but y equals 0 if and only if x is one of these values, means the graph goes through this point and this point. It also goes through the vertex. And if x equals 6, what do we get? We get 36 minus 72 plus 16. So the graph in this scale probably comes down like so. Didn't leave myself enough room to do this. Say 36, 16, 52, y equals negative 20. This is the point 6, negative 20, and y equals 16 up here. Scale doesn't work out real well, but that's just a synopsis of what you need to do in order to get the graph of a quadratic function. This is a little bit messy, but we're reviewing. If you don't understand exactly what you're seeing, you do need to go back and review this a little bit more. Okay. Okay, we want to express h of x. That's kind of a fancy h, I can't help myself. H of x equals square root of x minus 5 plus 5 as a composite function. Well, first of all, we have to know what a composite function is. That simply means a function like f of g of x. Okay, now that's also written f circle g of x. F circle g is the name of this composite function. But we also use the name h of x. But I'm not going to get into a lot of detail on that distinction. We want to do an f of g of x. So f of g of x to be the square root of x minus 5 plus 5. Now, the way I usually advise thinking about this, and there are other ways, is what's the first thing that happens to x? Well, you subtract 5. Okay? the first thing that happens to x is you do x minus 5. So it makes sense to do g of x. G of x to x minus 5. Then what happens to x minus 5? We take the square root of it and add 5. So I'm going to write this. F of g of x should then equal the square root of g of x plus 5. Okay, if I replace x minus 5 with g of x, f of g of x, in order to equal this expression, has to be then square root of g of x plus 5. If g of x is anything but x minus 5, this is going to equal this. So this is what gets a little confusing. F of x, well, f of x is going to be the formula into which you substitute g of x. Okay, so f of x had better equal the square root of x plus 5. Reason? If you replace x with g of x in this expression, this is the expression you get. So there we have it. We could say h of x equals square root of x minus 5 plus 5 equals the composite function f circle g, and I've been using script, so let's not confuse the issue here. Circle g of x myself writing below on the board, but in this form, f of x equals the square root of x plus 5 equals x minus 5. I intended to use the same expression, x minus square root of x minus 3 plus 5, so we don't confuse the two 5s, but that shouldn't be an issue. And you could convince yourself that if I use square root of x minus 3 plus 5, then g of x would have to equal x minus 3. F of x would still be the square root of x plus 5. Once more, if we replace x by g of x, that means we're replacing x by x minus 5, means this x would have to be replaced by x minus 5. And if it is, we get this expression. Okay, we want to find the equation of a straight line through the point -4, -6 with slope 4/3. Now there's a formula you can use, but I kind of urge that we understand the geometry of this situation. So y equals -6 here, and x equals -4. Here. Then we have this point. It would have a slope 4/3. Okay, well, this means, I'm gonna change this. So I want that to be 5/3. As it's an unfortunate consequence of using 4/3. Actually, I didn't need to do that, but that's okay with mine. Now, if the slope of this line is 5/3, that means if I move over 3 units, here, then I'm going to move up 5 units. Because of course the slope is rise divided by run. Run is how far you go this way, rise is how far you go this way, so we get a form here. So now we can sketch a graph. We would get an even more accurate graph if we moved over, let's say, 9 units. Okay, if we move over 3, 6, 9 units, we might be here. If we move over 9 units, we have to move up 15 units. So we move up 15 units, we get another point on the graph. But there's a reasonable sketch. Okay, now, let's suppose at this point, this coordinates x and y. Then the slope from here to here is going to be, well, how far is this? If this is x, this isn't, it has x coordinate that we just call x. Then from here to here is x minus 3 units. Then from here to here, okay. Now, I can write to statements. The slope is 5/3. That was given. Also, we have a rise of y minus 5. We have a run of x minus 3. So slope is y minus 5 over x minus 3. So y minus 5 over x minus 3 equals 5/3. Now, you don't have to know that to get the right answer. But if you know this, you have a deeper understanding of what the graph tells you, what this line tells you, so forth. You also have the formula. Y minus y1 equals m times x minus x1. Well, y1 is -6. Uh-oh. I've been doing a lot of the flipping. I don't know why it's 5. And I don't know why I wrote x minus 3, except I saw a 3 there. So let's correct this. Okay. Let's look at what the coordinates of this point are. This is xy, and this is x minus 4. So this would be x minus -4. The run from here to here. And this should be y minus -6 equals 5 plus 6. So that when I wrote my slope, that's apparently just pulling numbers that I'd seen on the board out of a hat without being very specific about what I was doing. Now, in class, I'll often say, well, I did that intentionally. See if you're going to catch me. But no, I didn't do it intentionally. Okay, I just did it. So the slope is what? Well, correct expression here is y plus 6. Correct expression here is x minus 4. So we get y plus 6 over x plus 4. Again, we're simply calculating or writing out the expression for the slope from this point to this point. To get from here to here, how far do we have to go up? Well, here we're at y equals -6. We have to go up 6 units. And then we got to go up y more units. So we got to go up y plus 6 units. Okay. And to get from here to here, we've got to go over, we're at x minus 4. So we've got to go over 4 units just to get to the y-axis. And then x more units. So we have x plus 4. Okay. Okay. Well, again, this gives us an expression for the slope. Rise divided by run y plus 6 over x plus 4. And that's equal to the given slope. So we get this equation. Now we can solve this equation for y and we get a perfectly good result. Okay. But if we use the formula, that's okay too. We get y minus y1. Well, y1 is the y coordinate at this point, which is -6. M is 5/3, because that was given. And then this will be x minus -4. Now, all that should look familiar because we just did it here, and here it is in the graph. This gives us y plus 6 equals 5/3 x plus 4. We solve for y. Now, to solve this for y, we have a denominator of 3. Whenever we see a denominator in an equation, or one or more denominators, we multiply both sides by the common denominator, preferably the least common denominator. So we're going to multiply both sides by 3. And it's obvious what we get. 3 here divides the 3. So we have 5 times x plus 4. Here we have 3y plus 18. Be sure we use the distributive law carefully. Well, I'm out of room, but we can easily solve this for y. Now we distribute the 5x, 5 through the x plus 4, we get 5x plus 20. Then we subtract 18 from both sides. And we get 2 on this side. And on this side, we get sorry, 5x plus 2. On this side, but we then would divide both sides by 3. We would end up with 5/3 x plus 2/3. That's reasonably compatible with our sketch. The y coordinate looks a little bigger than 2/3 here, but the graph wasn't carefully scaled. Okay. Now, my point is, if we solve this equation for y, we get this. We multiply both sides by x plus 4. And notice that this is exactly the equation to get from the formula. So there's a picture that fits the formula. Now, in your course, you're probably not going to be required to produce this picture and to understand the formula. What I do recommend you do is understand that a graph can give meaning to the symbols. And in your subsequent courses, you're going to understand things that you would otherwise understand, make an effort to understand how the symbols relate to the graph. Okay, my class just showed up 15 minutes late, but oversleeping and other sundry things. At least one person showed up. and uh, yeah, that person's always here and almost always, at least almost on time. So, we don't have somebody who's been slacking, okay? The rest of the class, they haven't been slacking either, but they're mostly not here right now. Okay, so just to summarize what we've done so far, the domain and range of this function, we can't take the square root of something that's negative, so x minus 3 has to be greater than or equal to 0. Now, I say we can't take the square root. We can take the square root. We could get an imaginary number if you have a negative under here. But we're talking implicitly about real numbers, domain over real numbers, the range over. And if you get into complex numbers, well, you don't want to go there. You need about 5 more years of intensive undergraduate study before you really understand that. Okay. So we say the square root of x minus 3 has to be greater than 0. And also, okay, well, it's two different things. Square root of x minus 3 has to be greater than or equal to 0. And what's inside here has to be greater than or equal to 0. Okay. When you take a square root, you can't get a negative number. Because if you multiply a negative by a negative, you get a positive, and that means you can't get this. If you take a square root, you can't get a negative number. Okay, so x minus 3 has to be greater than 0, and x minus 3 can take any value, but it only works if x minus 3 is greater than or equal to 0. Now, it only works then if x is greater than or equal to 3, which should be obvious. If x is less than 3, it's going to be negative. Not going to work. But there it is, more formally. Then, coming back to our observation that x minus 3 has to be positive, that means it has to be non-negative. It can be 0 or anything greater than 0. But if you add 5 to something that can be 0 or greater, you're going to get something that can be 5 or greater. And there's your range. Now, we can go through the process here to prove that. In my class, probably going to ask you to prove this thing, but you never know. It might be there as an optional problem. So what we do is we take y equals square root of x minus 3 plus 5, assuming that y equals f of x, and solve for x. Well, when we solve for x, we get x equals y squared minus 10y plus 28. And the steps are simple. This is quadratic. If it was a quadratic function, it would have a quote vertex at negative b over 2a equals 5, something we should understand if we know the quadratic formula. Okay. And the parabola would open upward because we have a positive coefficient of y squared. Now we're used to parabolas where we do y versus x. Here we're doing x versus y. Okay, because x equals this. But we're still going to, the horizontal axis is going to be our independent variable, that's y. And the vertical axis is going to be our dependent variable, x depends on y. So we're going to have y here and x here. And if we graph this thing, well, the vertex is at y equals 5. So here's a line y equals 5. That's going to be the axis of symmetry for our function. And then if y equals 5, we plug 5 in here and we get 3. So that this point is y equals 5, x equals 3. And all the values we get for x are greater than or equal to 3. As the parabola rises above the vertex. Okay? And it includes vertex. And from this, we could conclude that the domain is free infinity. But that's a little more work than I really have to do. Now, depending on how much time I have, I might put a number of optional problems on the exam, and that might be one of them. But that's for my class. And for general classes, well, in general, you might have to do this sort of analysis. And then I graph y equals x squared minus 12x plus 16, just using the standard analysis. We do the quadratic formula, and we get this, which simplifies to 6 plus or minus 2 square root of 5. Okay, well, the 6 comes from the 12 over the 2. 12 is your negative b. There's your b, it's negative 12. You put 12 here because that's negative b. And the denominator is 2a, which is 2 times 1 in this case. So there's your negative b over 2a, which will be your vertex. That's x equals 6. Then we approximate square root of 5 by, I think, 2.23. Okay. And, goes on from there. So we'll say twice that is pretty close to 4.5. So 6 plus 4.5 is 10.5. 6 minus 4.5 is 1.5. So we have the line x equals 10.5 here. The line x equals 1.5 here. Those are the approximate zeros of the function. So the graph has to go through these points, has to have a vertex on this line. We know it's going to open upward because x squared is positive, has a positive coefficient. So we plug x equal x into this, and if I did my arithmetic right, we get y equals negative 20. So here's a line y equals negative 20. It's kind of messy. If it's down here, there's your vertex. Here are your zeros. Your x-intercept would be your y-intercept occurs when x is 0. That would give you 16. So it's not particularly accurate. This point should be a little higher if this point is this. You get the idea. Okay. So let's kind of review how you graph a quadratic function. Then we express h of x equals square root of x minus 5 plus 5 as a composite function. Now, I've been through complete discussion that composite function means this h of x should be f of g of x, or some f and some g. Question we ask is, what's the first thing that happens to x? We subtract 5 from it. Well, what's the first thing that happens to x here? G acts on it. Okay? So g of x could be x minus 5. So we let g of x equal x minus 5. Then what is f of g of x? Well, it would have to then be the square root of g of x plus 5, because g of x is x minus 5. This is g of x. And we then conclude that in order to get an f of x such that substituting g of x for x gives us this, f of x is going to have to equal this. If we plug g of x in for x, we get f of g of x equals square root of g of x plus 5, which is just what we wrote here. Okay? And since g of x is square root of x minus 5, then we get this. Then we say f circle g of x, because f circle g is the name of this function. F of g of x is how we calculate the composite. H of x equals this function is f circle g of x if f of x is the square root of x plus 5, square root of x plus 5, and g of x is x minus 5. And we find the equation of a straight line through -4, -6 with a slope of 5/3. And I did that first geometrically. Here's the point where x equals -4 and y equals -6. Slope of 5/3 means rise of 5 when the run is 3. So we take a run of 3 and go up 5 units. Now, at this point, we would have a second point on the graph, and we could use a formula for that, but just geometrically, that's how we can sketch an approximate graph. Turns out my slope is a little too steep here because of the way the y-intercept turned out, but that's okay. And well, then if I put the point x, y in the graph up here, where x, y could be any point on this line. The run from x equals -4 out over to x is just x minus -4, which is x plus 4. From here, we need to go 4 units to get to the y-axis and another x units to get out to the point xy. Similarly, y coordinate is y here, it's -6 here. To get from here to here, we go y minus -6, which is the same as y plus 6. 6 units to get here, y units to get here. From this, we can write slope is 5/3, but the slope is also y plus 6 over x plus 4. So y plus 6 over x plus 4 has to equal 5/3. And we can easily rearrange that, multiply both sides by x plus 4, we get this. That should be obvious. Now, there's also the formula, y minus y1 equals m times x minus x1. It's perfectly all right to use that formula. But I like to emphasize the graph because the better you understand graphs, the better you understand what the graph is telling you about a function, the better you're going to understand what you see when and if you take a calculus course or any other math course, as this course is a prerequisite. Okay. So if we use this formula, well, we just plug in. We plug in -6 for y1, is x given point, and -4 for x1. That's the x coordinate of the given point. And we get this, which is the same thing we got here. So this picture gives us this, and the formula gives us this. There's a reason for the formula, and the reason for the formula is the picture. At least if you want to think geometrically. Okay. Okay. I want to talk about polynomials. Example. Y equals this, and that of course equals, I think, x cubed, then it's -2 minus 4 plus 5. So I think it's minus x squared. I might be doing this wrong. And where this is the number that goes in front of x, and this is the number that's left over, and I don't want to try to multiply that in my head. Okay. I could ordinarily do that, but it takes a little while to have to stand here and fumble over. You can multiply this out using the distributive law and should know very well how to do that. If not, practice it. So zeros and y equals 0. So that means x minus 2 times x plus 5 times x minus 4 equals 0. And that's going to be true if x minus 2 equals 0. If x plus 5 equals 0. And if x minus 4 equals 0. So anytime you have a product of 3 or more things equal to 0, your solution would be any x that makes any one of those 0 works. So it could be this, or this, or this. I emphasize writing out that or because it just helps clarify your thinking. one of the benefits of mathematics, even if you don't use it a lot in your future, is it sharpens your thinking. Okay, so clearly then x would be 2, or x would be -5, or x would be 4. So that if we want to construct a graph, this polynomial, have the point x equals -5. We have the point where x equals 2, the point on the x-axis where x equals 2, because the y coordinate will be 0. That's a premise. And x equals 4. So we have these three zeros. Now the y-intercept equals 0. Well, we get y equals 0 minus 2 and 0 plus 5 and 0 minus 4, which is just -2 times 5 times 4, which is times -4, which is 20. It's 40. So our y-intercept will be up here. Y equals 40. Now, long run behavior, depending on the language you prefer, the language which text uses, or your open math videos, okay? You might see both one in one place, one in another, but the end or long run behavior is like y equals x cubed, because x cubed is the leading term, the highest power term. And what does y equals x cubed look like? The graph of y equals x cubed. This is one of our graphs. It looks like this. Okay. So the way I like to describe the graph of this function is, if you zoom way back, the graph pretty much looks like this. But in here, close to the y-axis, like at these x values, it wiggles a little bit. Okay. Now that's just an arbitrary wiggle. The exact wiggle we have, well, x cubed is going to go to -infinity as x goes to -infinity. And you can figure that out numerically as well. And you should understand why that is. Because if you cube a big negative number, you're going to get a really huge negative number. Because when you cube, you're multiplying the number by itself and then by itself again. Okay? Now, if you multiply a negative number by itself, you get a positive multiplied by a negative number, it gives you a negative. It's going to be really big. As you go to the left, x gets really big but negative. Okay, so we can draw a little arrow down here indicating that to the left it goes negative. And similarly, you can conclude that to the right it goes positive. It has to go through these 3 points, 4 points. So it's going to end up looking something like this. If you've got I'll use the same 0, y minus 2 times x plus 5 squared times x minus 4 cubed. Okay. same as before. The y-intercept, well, if x equals 0, it's going to be at -2, and then times 5 squared, and then times 4 cubed. And look at what I've got myself into. I've got a -4 cubed. I've got to multiply that out. Well, 2 times 5 squared is 50. 4 cubed is 64. So that must be 32. And it's going to be positive. Now let's make sure 60 times, yeah. Okay, I think that's 3,200. So that changes the scale of our graph a lot. We're going to want to still put the y-intercept about that far above the x-axis, but now it's going to stand for y equals 3,200. So this is going to have crazy values. So we get this. The line x equals -5, and the line x equals 2, and the line x equals 4. So we got zeros here, here, and here. Still on screen. Okay, good. Now our long run behavior. Well, if we multiply all these out, we're going to get an x from this. If I multiply this out, I'm going to have x squared plus 10x plus 25. It's going to have an x squared. But multiply this out, I could say it, that it probably won't. I try to say it has to be x cubed, because we use a distributive law to multiply it out. We're going to get an x cubed. So we're going to have an x times an x squared times an x cubed. Now, x times an x squared is going to give us an x cubed, and multiply it by x cubed, we're going to get an x to the 6th. That means that our long run behavior is going to be like y equals x to the 6th has got a graph that looks like this, kind of like a parabola, but it gets really flat down here. Stays flat longer than a parabola does. Okay. That means it's up here and up here. So it's going to have to go up this way. It's going to have to go up this way. Okay. Well, how we're going to start up here and go through this point, and the y-intercept, which I said was y equals 3,200. How we're going to go start up here, get through this point, and then come back up to this point. If we go through this point, we have to come back up before we hit another 0, and we can't. The only way this is going to be 0 is if x is one of the 3 values, 2, -5, or 4. Well, the answer is the 0 at x equals -5 comes from x plus 5 squared, which means that close to this point, this value and this value don't change much. But this is a square. This is quadratic thing. It's approximately quadratic in this vicinity. So it's probably going to come down something like this. And just like a squaring function, it's going to have something like a vertex here. It's not going to be a perfect vertex because this and this do change a bit. And if we move very far from x equals -5, they change a whole lot. So it's going to do something like this. Okay, then it's going to come up and go down through here. Then it's going to go to x equals 2. Well, at x equals 2, we have x minus 2. So close to this point, this looks like a multiple of x minus 2. So we're going to go straight down through here. And now I'm in big trouble. Never mind. Not big trouble. I just don't think really. Okay, then we get to the 0 at x equals 4, and that's q. Well, what's the graph act like near q? it acts like this. It levels off for an instant and then it just goes on. So a graph is going to look like this. Now, I don't know what just happened. Okay, the screen looked like everything was in focus. But then when I moved, so apparently the screen was fixed on me or I wasn't seeing it clearly. Looking at it from a distance, sometimes I don't see it. Let's make sure we understand what I just did. For this function, we found the zeros where x could be 2 would make this 0. Alternatively, x equals -5. So I say or x equals -5 or x equals 4. Question is, where is this 0? At this value or at this value or at this value. Okay. So we sketch those 3 points on the graph. We get the y-intercept by substituting x equals 0 into this, and it's very straightforward to do that. If I did it correctly, we get 40. The end behavior, if I expand this, it's like an x cubed function done with a bunch of other stuff on it. When x gets really big, x cubed is the only thing that matters very much, so that the graph is much like a y equals x cubed graph with little wiggles near the y-axis. This is what the graph would look like if you zoom way back. You don't have to go that far back before it pretty much looks on this scale. Maybe we go back to where 100 is out here. So, okay. And then the wiggles that we see here become first. So anyhow, we get this graph. Since we're sort of embedded in this x cubed function, it goes down here, it goes up here. And it approaches negative infinity on this side, positive infinity on this side, and we can easily draw a curve. If I change the exponents, same factors, but the square of this one and the cube of this one, the zeros are still going to occur where they did before. The y-intercept, well, if we plug in 0, we're going to have to square the 5 and cube the -4 and multiply it all out. And I think we get 3,200. You can check the numbers. So we do our x-intercepts. Our y-intercept, label that y was 3,200. And we observe that the long run is going to be like x to the 6th, because from this we get just an x. Here, x is going to end up being squared. We're going to have x squared plus 10x plus 25. But the point is we'll have a leading term of x squared here and a leading term of x cubed here. If we multiply an x by an x squared by an x cubed, we get an x to the 6th. So the leading term is going to be x to the 6th. So this is going to act like the graph of y equals x to the 6th in the long run. It means we got to go up here and up here. At this point, this occurs because the x plus 5 squared, as I explained, that means you're going to have something like x plus 5 squared here, but vertically stretched by whatever these values are in the near vicinity of x equals -5. At this point, that would be x minus 2 times whatever it is. That'd be a vertically stretched x minus 2 graph, which would go straight through the axis. And at this point, it's like x minus 4 cubed, so it acts like a cube graph. So we come down from here, we turn around here, we come up through here, down through here, we come up here, flatten out, and then we move on up. Okay, so I don't know if that was in focus or not, so I really wanted to go back and say it all again. Okay, I'm gonna dive right in. And actually, this is a continuation of what I did the MBE support class. I'm just doing kind of a review of the high points of the course for mine. Okay, so I'm just going to very quickly point to things that I did previously, but I'm not going to talk about it in detail. because it's on the video. Okay, I want to remind you. So, first thing I did was express this function h of x equals the square root of x minus 5 plus 5 as a composite function. So we want h of x to equal f of g of x. That's what it means to be a composite function. So f of g of x should be the square root of under the x minus 5 plus 5. What's the first thing that happens to x? Well, g of x is the first thing that happens to x. What's the first thing that happens to x here? We subtract 5. So we let g of x equal x minus 5. So f of g of x then is equal to the square root of g of x plus 5. Well then, if we just replace g of x by x, we get the formula f of x is square root of x plus 5, such that when we replace x by g of x, we get this, which is this. So that's a kind of logic that would be good to understand. I said it really fast, probably don't have time to process it, but it's worth thinking about. And I'd go over it in a lot of detail. In any case, we then say h of x is square root of x minus 5, 1 plus 5. And that equals f circle g of x, because that's our notation for the composite function. It just means f of g of x. Where f of x is square root of x plus 5, g of x is x minus 5. We do a straight line through a point with a given slope graph. We can locate the point. The slope is 5/3, so from that point we can move over 3 and up 5, get another point, which gives us a line. We put a point xy anywhere on the line. Then the slope from here to here, well, the rise from here to here is y minus -6. We're going from -6 up to 6. Rise is y minus -6. Similarly, the run is x plus 4. So we can say the slope is 5/3. We can also say the slope is y plus 6 over x plus 4. If the slope is this and the slope is this, then this has to equal this. So we write that as an equation, and we can solve that equation for y. We start by multiplying both sides by x plus 4, and we go from there. Now, if you use the formula, it's y minus y1 equals m times x minus x1. Okay, and we plug in -6 for y1, 5/3 for m, -4 for x1. We get this, and we use the distributive law on this side at least, and we get this. This is the same as this. So we then solve this just using simple steps. You get y equals 5/3 x plus 2/3. Might be a little hard to see. Maybe I can write that out. And that gives us y-intercept of 2/3. Now, if this is 4 units, this looks more like about 1.5, maybe even almost, well, about 1.5 units, not 2/3. But of course, this is a hand-drawn graph, and I got it just a little bit too steep. I went a little too high. Or maybe I did go over far enough, but that doesn't matter. Okay. So the main point here is you have this formula, that'll get you the equation. But here's what the equation means as you go on into more advanced courses. It's very helpful to be able to think both about symbols and the picture. So let's make that. Now again, that's, if you look at the video, I'll go over it in more detail. Get the domain and range of f of x square root of x minus 3 plus 5. What it comes down to is x minus 3 can't be negative. So x has to be greater than or equal to 3. Also, square root of x minus 3 can be 0, but it can't be negative. So it can be any number from 0 on. And when we add 5 to it, it can be any number from 5 on to infinity. So the domain is the interval 3 infinity. The range is the interval 5 infinity. Both those intervals half closed. If we include 3, we include 5. I do this mysterious thing, which I probably won't put on the final, but it's worth seeing. So all I've done here is I've let y equal f of x, so y to the square root of x minus 3 plus 5. I've solved this for x, and I got x equals y squared minus 10y plus 28. Well, y squared minus 10y plus 28 is a quadratic function. If we were to graph x versus y here and x here, the vertex would be at negative 10 over 2 times 1, or 5. Out to negative with negative. The negative b over 2a would give us the vertex. We plug the coordinate of the vertex into the function and we get the value 3. So the vertex would be at 5, 3. The x values, which go this way here, are then 3 or greater, which corresponds to the domain. And the range is from 5 to infinity. And we don't reason that out necessarily from this picture. It says something. Here, just for comparison, I go through the graph of x squared minus 12x plus 16. Quadratic formula gives us 12 over 2 times 12 plus or minus the square root of all this stuff. Comes out 12 plus or minus the square root of 80 over 2. And that is 12 over 2 is 6. Square root of 80 over 2 is 2 square root of 5. Because 80 is 16 times 5, square root of 16 times the square root of 5 is 4 times the square root of 5, and you divide that by 2, you get 2 squared. And that's approximately 10.5 or 1.5, and here's a picture of the graph. So I go through the details of that. Now, more recent thing that I did. Talk about polynomial. Here's a polynomial. If we expand it, we're going to get an x cubed. I think we'll get a negative x squared. I didn't want to take the time to figure out these numbers, so I just put an incoherent shape there. If zeros occur when y equals 0, set this equal to 0, and you're going to get x equals 2, or x equals negative 5, or x equals 4. I explained the details a little bit earlier in the video, if you want to see that. The y-intercept occurs when x equals 0, and let x equals 0 here, and you're going to get 40. So you have a graph. Y-intercept is 40. X-intercepts are negative 5, 2, 4. The end behavior is like x cubed. X cubed has a graph that looks like this. If you zoom way back on this graph, it looks like a graph of x cubed. If x is 100 out here, let's say, then whatever your y scale is, your graph is going to look like this, but you're going to have little wiggles like you see here, close to the origin. And if you're 100 out here, well, this is it. These wiggles would occur between negative 5 and 4, just real close to the y-axis on this scale. And there's your graph looked at from a distance, which means the graph has to go to negative infinity this way and positive infinity this way. So you have narrow down, narrow up, and you draw. Now, in a minute, I'm going to do rational functions. You want to be sure of my this. Okay. Another example, same factors, but square this one, cube this one. What's that do? Well, one thing, we're going to get an x out of this, an x squared out of this, and an x cubed out of this. Go ahead and do this using the distributive law, and you'll find that that's true, if you're not convinced of it. Okay? So the graph is going to look like y equals x to the 6, which looks a lot like y equals x squared, being an even power, but it's much flatter toward the middle. And then it's going to have wiggles in here, and these are the wiggles. Now, why do the wiggles look like this? Because when x equals 2, you've got the x minus 2 function, which is a linear function. You go through this one linearly. I explained that in more detail earlier in the video. But just refreshing you, I'm not saying anything I haven't said half a dozen times already during the course, okay? This is squared. So near x equals -5, you have simply a multiple of x plus 5. Now, the numbers you get here and the numbers you get here change a little bit as you move to the left and right of x -5, but they don't change that much. So your graph is basically very close to this point, is basically a vertically stretched squaring function. So you're gonna come down from here because of the long run behavior. You got to come down from above and you turn around. And then you can go up and through the y-intercept. And then you come down and the next zero that occurs is at x equals 2. Well, we already saw that's linear. And then you got to go through this point. You don't go straight through it because x -4 is cubed. And just like near x equals -5, this acts like the x plus 5 squared function, but vertically stretched. This one is a vertically stretched cubing function, and it's going to flatten out and then go up, just like a cubing function. Okay, so that's a quick synopsis of the first I don't know, maybe probably not quite an hour of the video that's going to be posted. Okay. Now I want to go on and talk about rational functions, talk about exponential functions and logarithms, and just hit the high points, just to give you a perspective and an idea of what you might need to review for the final. Okay. And then, a quick synopsis of matrices, augmented matrices, matrix multiplication. We're not going to go through details of that because we've been doing details of that for the last week and a half. Okay. Well, let's take a function very much like the one we've already done. Okay, this is a rational function. It's a polynomial divided by a polynomial. Now, one thing that I'm not talking about right now is how you factor a polynomial. You might have to factor a third-degree polynomial. Remember that you find a number that makes it 0 and do a long division x, but with x minus that number. Okay, so you want to review that. I'm not going to give you fractional things that have fractional roots and expect you to find them. But if you can do that much, you can reduce the cubic polynomial to x minus something times a quadratic polynomial. And then you know how to find the zeros of a quadratic. Just set it equal to 0 and use a quadratic formula. Or if you're lucky, factor it. Okay? Well, anyhow, so I'm not going to go through that. There just isn't time. But make sure you review that process, which people were doing pretty well back when we did it. Okay? So we have this. This is a rational function. I'm not going to label it. A rational function is a polynomial over a polynomial. Zeros are at 2, -5, and 4. So already we have information that we can put on our graph. Well, okay, there we go. Now, those are zeros of the function. You do have to be careful to make sure that none of these zeros are also zeros of the denominator. In that case, you would have to simplify your factored function. So we'll assume this might have been something that had even higher powers, but when it's simplified, it comes down to this. Okay? If you divide out a zero of the denominator, that gives you what you call a removable singularity. Okay? You've seen that. I haven't talked too much about it because this process has been challenging enough for me. The key thing that not everybody has seen yet is you have to distinguish zeros, the numerator. And those zeros will occur when x is -3 or x equals 6. And these correspond to vertical asymptotes. Now, usually we indicate vertical asymptotes with a dotted line. And I'm already using dotted lines to label my x's so that I can put my labels down here where they don't interfere with the graph. Okay? And I've kind of stressed the wisdom of doing that. It does complicate things a little bit with vertical asymptotes, but I'll just use a different kind of dotted line. Okay, so x equals -3, that's here. I use alternate long and short dashes to indicate a vertical asymptote at x equals -3. And then another one out here at x equals 6. Okay. Now, you have long run behavior, and it's like x cubed over x squared. Because if you zoom way back, this is like x cubed, and this is like x squared. Okay? All the lower powers become insignificant compared to x cubed and x squared. Equals x. Now you do get a slant asymptote in the case where the long run is like x. Okay? We have to do a long division, divide the denominator into the numerator, and you would first have to expand this using the distributive law and expand this using the distributive law. Okay? And you would end up with a linear function. I'm not going to sketch that asymptote. I'm just going to say that it's going to do this and the long run. It's not going to go real steep. It's going to stay kind of linear. So that what you have here is you're going to have a function that pretty much, if you zoom way back, is a linear function that goes through the y-axis reasonably close to x equals 0. Okay, well, what is the y-intercept? I didn't leave myself room to write it, and I'll say, okay, the y-intercept at x equals 0, and y is going to be 0, -2, which is -2 times 0 plus 5 is 5, and 0 minus 4 is -4, over 0 plus 3 is 3, 0 times -6, 0 plus -6 is -6. Well, that equals what? -10, 40. This is -18. So it's -40 over 18, which is -20 over 9, which is approximately 2.2. So your y-intercept is 20 over 9, which is approximately 2.2. And this tells us that the slant asymptote might well be x plus 2.2. It's the 45-degree line through here. Okay. Now, not worrying much about the slant asymptote, although you will have an opportunity to do a slant asymptote and show that you can. Okay. It's not going to be a really big deal on the exam. I don't recommend necessarily that you skip it if you understand it reasonably well, which I think many of you do. But it's probably only be a couple of points in the whole exam. Okay. And it was covered. You did it in your homework. It's probably not your top priority for reviewing. You're going to have to judge what you have time to review, what you take the time. Okay, so anyhow, we got to go through this point, this point, this point, this point. We got to start down here, get up through this point, come down through this point, come up here and go out this way, right? Except we've got these asymptotes. And at the asymptotes, well, at x equals -3, this thing is a lot like 1 over x plus 3 multiplied by all the rest of this stuff. What is a graph of 1 over x plus 3? Well, it's a graph of 1 over x. That's a reciprocal graph, shifted 3 units to the right. Okay. And I said 3 units to the right, 3 units to the left. Okay. So at x equals -3, this thing acts like a reciprocal graph. Got to do something like this, something like this. Maybe you have to flip this about the line x equals -3. It's like reflecting through the reciprocal function through the y-axis. And at x equals 6, it's going to be the same thing. Might be like this. Flip vertically around this line. So let's see how this works out. Okay, if we come up from down here and through this point, then we're going to have to approach this as an asymptote. And that means that we're going to come up something like this. And approach it here. So it is flipped. And I've got kind of a problem. Something's wrong. Because if it's acting like a reciprocal function, it's got to come back up through here and go through this point. Pause for a minute. Reconcile this because this gets tricky. It's a little surprising because it's not that complicated, but. Okay, I had to review what I've done, and what I done is this is negative 20/9, and then I got the 2.2, and it wasn't any strain, but it was enough of a strain. I forgot to write my negative sign. So I have to correct this. You see that this isn't making any sense because this has to be like a reciprocal function, which means it has to come up from here. It can't come up from here and go through this point, can it? Because there's no zero. Get rid of that line. That's like down to this and everything else up. Then I've got to get rid of this curve. Oh, it's a little smudge, but apologies for that. The y-intercept has to be done. So now it's fine. I didn't have to get rid of that part of the curve. Wasn't thinking when I did that, because now I can flip around here. Come up from this negative asymptote, and I can go through here, and I can go through here, and go through here, and come back down. So coming up from here, approaching this asymptote, and then from here, I can come down some point, then I go back up and approach probably this line as an asymptote. Now, there's a lot in that. It's best if you thoroughly understand why polynomials work. Then it comes down to something that's actually fairly simple if you just keep your wits about it. Find the zeros of the numerator. Those are going to be zeros of the function, assuming this function has been simplified. Find the zeros of the denominator. Those will be vertical asymptotes. Add an x plus 3 squared here, then the asymptote would have to approach, the curve would have to approach the asymptote on the same, I want to say on the same side. I'm not going to say it. All I'm going to say is that a vertical asymptote might look like this. Just depending on whether it comes from an even power or an odd power. Of course, you should understand this graph. Reciprocal square graph. You should understand all of the toolkit function graphs. All right. So there's a synopsis of most of what you need to know for rational functions. I went any deeper into it. Well, need to go as deeply into it as the homework does. Okay, and the quizzes. Just a quick note, speaking of the final, it's always a good idea to go back to the videos and review the quizzes. They're right at the beginning of each video, so you don't have to watch a whole lot of video to see what the quiz was and remember if you know how to do that or not. And if you don't, then it gets explained. Okay? It's a real good place to start review. Now, the quizzes aren't totally comprehensive, but if you understand what's explained on every quiz and can do it on the test, you're more or less reasonably assured of at least passing grade. Okay? Better than a D. All right. Well, again, it's a pretty brief synopsis, but that's the best we can do in the time we have. So exponential functions. Y equals AB to the X, or Y equals A times 2 to the KX, or Y equals A times E to the KX. Okay, those are your basic forms of exponential functions. Now you can always add a number there, and that number will give you a horizontal asymptote. Okay, so just a couple of examples, just what they look like. Y equals AB to the X, of course, as a graph, as do any of these, it might look like this, or it might look like this. And if A is negative, it might look like this. So negative A would be here or here. B greater than 1, A greater than 0, give you this graph or this graph. Less than 1 and has to be greater than 0 because you can't take an arbitrary power of a negative number. B, this graph or this graph. Okay. Now you should try to understand why that is. Try to address it a little bit. But the graphs are going to have one of these shapes, maybe steeper, maybe less steep, and they can all be constructed the way we constructed the graph. Okay. And of course, you do need to be able to do those standard constructions and that problem that I think is kind of the first problem in every test we've had so far. Okay. Expect you to be able to do that. Construct this thing with the red dot where I say it. Give me the formula function and all that stuff. Okay. So if y equals c, then this graph, for example, would be y equals a b to the x plus c. If b greater than 1, or a e to the kx plus c, or a times 2 to the kx plus c. Where k is greater than 0. It's worth thinking about what I'm telling you there. Okay. Also, a positive. Now, just for contrast, if A was negative, you might have a graph that looks like this. Okay. Now, there's your exponential functions, logarithmic form. X equals C is equivalent to X equals log base B. C, because inverse functions. That's the most basic thing you would remember. Okay. Now, logarithmic form, you'd have to solve this for b to the x. You get b to the x equals y over c, y over a, so that x is base b of y over a. In this case, 2 to the kx would be y over a. So you would get ax equals log base b y over a. And here you would get kx equals the natural log of y over a, because there'll be log base e of y over a, but log base e is the natural log. Now, I just kind of list these to remind you of this correspondence, but you should understand how this rearranges to this. Simply get your b to the x or 2 to the kx or e to the kx alone on one side. What's on the other side in each of these cases will be y divided by negative. And then the form gives you exactly what you need. Okay. Now, half-life of an exponential function. As I'm sorry, I'll do Delta time first. B to the x equals 2, or 2 to the kx equals 2, or e to the kx equals 2, depending on what form of the function you have. If you solve this equation and find that x is negative, then it's a half-life. Okay. So for example, if x is -5, you would have a half-life of 5. I could write out a rigorous definition of that, but then you'd have to process it. So just for example, if x equals -5 implies I want to relate this now to the graph of the function. If you construct the graph of the exponential function, and each of these intervals is the doubling time. So for example, I told you that the doubling time of your investment was 8 years, then you just have to label this graph in increments of 8. Like if t equals 0 here, t equals 8 here, t equals 16 here. And if you know your initial investment, that's the y coordinate here. Okay, so it becomes very easy to sketch a graph and visualize. Make sense? Now, if you do the opposite, it's very easy. Sketch the graph of an exponential function with a half-life. Still put the red dot here. And we move right to left instead of left to right, because when you replace x by -x, that flips things around the y-axis. There's a connection there that I'm not going to take time to explain, but I'll just tell you that now there's your half-life. Now come back to some of this. Just a quick example. So you got y equals 40, t equals -32, and there's a point, your point on the graph. And then over here, have the points. Sorry, -32, 40. Your exponential function the declining curve is moved to the right, you get less, but and you approach the x-axis as an asymptote. So you can kind of do that just by sketching the smoothest possible curve you can through those 2 points that approaches the x-axis. In a sense, that's what the exponential function is. If x equals, or sorry, if y equals a, b to the t, and a and b. Okay. Now I'm abbreviating this because we've done it fairly loosely. Plug in the coordinates of the 2 points. You get 40 equals a times b to the negative 32. At this point, you get 5 equals a times b to the 16th. Okay, so from the first equation, you get a equals second power. And then plugging that into the second equation, you get 5 equals 40 b to the 32nd times b to the 16th equals 40 times b to the 48th power can't get it one kind of person to have this. This tells you that b to the 48th equals 1/8. So now you go to your calculator and do v to the 1/8, b equals 1/8 times cyclical 48th power. Or if you wish, the 48th root. And then you plug this back into either equation and you get the value of A. Okay, well, I'm not going to go through the details of that because they take too long. And I'd have to estimate b 1/8 to the reciprocal 48th power. And I'm just not able to do that today. I'd have to think. And I want to take the time. Just reminding you, if you have 2 points, you can write out 2 equations and solve them. And we've done that several times. And open math is had you do the same. Okay. Then the half-life, well, you can determine the half-life by setting b to the x equals 2. Or b to the f equals 1/2. B to the x equals 1/2. Once you have the half-life, you can sketch the graph. This or this. Okay. Now, this is the sort of thing that you do for an application problem. In any application, in a typical application, given given two values of y, you give values y for two values of x. Population of this herd is 738 in the year 2016, and it was 356 in 2004. Let your time be measured from a convenient point like 2000, and you'd have 2 points on a graph. So I always recommend when you're given information, you put it on a graph and then do what makes sense. Okay. And this should make sense because we've had to do it a number of times fairly recently. All right. Now, if you've got the equation, you can find the half-life. Or the doubling time. At that point, it's very easy to draw the graph. It's going to look like this. Since you're not going to shift the graph, you can eliminate the red dot and you can label the y values any way you wish. Okay, so you can always get a good shape of the graph. You label the half-lives like so, and you label y in a way that's convenient to you. So I recommend you be able to do that. But unless I give you some fairly explicit instructions for how to do that, I won't ask you to do that. I think it would be handy. I think it gives you insight. I think it would be very beneficial for you in future courses and other places, because exponential functions occur all the time. Okay. In all fields. Very common. Incidentally, sugar slows blood breakfast. All right. That's kind of this idea of applying an exponential function and doing this sort of thing and then answering questions about the function. Okay. Want to be able to do that. Now, find when the function has a given value. Example. Y equals 500 e to the 0.04 t. When is y going to be 800? If I would take the question. Well, y equals this, y equals 800, so this should equal 800. So you get this equation, right? And then e to the 0.04t is 800 over 500. 0.04t equals 1.6. Okay, so log base e of 1.6 equals 0.04t, or 0.04t equals the natural log of 1.6. So the t is the natural log of 1.6 over 0.04 equals, use your calculator. Okay. Now, natural log 1.6 is kind of close to 1/2. And if you divide that by 0.04, I think you get about 12.5. But I'm not going to write that down. Okay. Plug it into your calculator. And see if my brain halfway functions. Okay. And it'd be a little less than 12.5, because that's a little less than the square root of. I'd say around probably between 11 and 12, pretty close to 12. Okay. That makes sense? Stuff you've seen pretty recently. And you had that big assignment on, lots of problems with applications. Recommend you review that one, because there's almost certainly going to be something like that on the test. Okay. I think it was like been even section 1 of the chapter, but you can review it and locate it. You should review everything. You should look over the open math assignments, see if there's anything significant that you've forgotten. Just take a quick flip through them, make some notes, and review accordingly. Have logarithms and logarithmic and exponential equations, okay? You want to review that. I'm not going to take the time to go over the rules for logarithms and stuff, but you need to review them and be able to use them. Okay, so review. Logarithmic equation. This is the high points. Systems of linear equations and matrices. Well, that's what we've been doing very recently. Okay, so to solve a system by elimination. And that means, for example, and I'm just going to do a system of two equations and two unknowns. Okay, so we got system works. Okay. I'm going to choose to eliminate X. I could also choose to eliminate Y, but I can use smaller numbers to eliminate X. I multiply equation 1 by 3. This, I multiply equation 2 by -4, I get this. Numbers to the right. Yeah, okay. Okay, so we get 38y equals 76. Yep. Okay. So y equals 2. And we plug y equals 2. We get 4x. So 6 times 2 equals 16. So your solution. Open math has you express the solution as an ordered pair. It'd be 1 and 2. You want to confirm that solution? I can graph these two equations fairly well by intercepts. If y equals 0, x is 4. This equation. And if x is 0, y is 2 2/3. It's very straightforward to get that. So here's a nice straight line. Okay. A little wavy. My intercepts here are going to be -7/3, which is -2 1/3. That's the x-intercept. Okay. -2 1/3 would be up here maybe. That should be a little further over than. And y would be 1 point. Okay, y would be 1/5. And I'll just write y 7/5. So we would have these 2 points. And I made the line a little high. So I'm not going to get a great estimate. But this looks like it might be 2.5. And a little over 1. The line should be lower. And what we should get is y equals 2 and x equals 1. So x equals 1 might be here. And y equals 1 would be like about here. So the intersection point should really be here rather than here, but we're reasonably close. The point is, we can easily sketch an approximate graph and hope we're close. My -2 1/3 should have been a little further over. My line was a little too high, so that this intersection point will move over this way and down a little bit. Okay. And it'll be more accurate. It wasn't a very accurately drawn graph, just indicating this is the process that I've recommended. Okay. If you got three equations, three unknowns, you choose a variable, whatever variable is most convenient, and eliminate it. And then you get two equations and two unknowns, and you solve those and go from there. Okay, the augmented matrix. Okay, I'm going to divide row 1 by 4. That'll give me 1. I'll use decimals 1.5 and 4. In the second row is 3, -5, -7. Now from here, and I'm going to keep row 1. Row 2 would be multiply this by -3 and add to this, we're going to get 0. Remember, we want to get a 1 here, a 0 here, a 1 here, and then ultimately a 0 here. So we're going to have 1, 1.5, 4. And it's going to give us 0, and I'm just going to do it, kind of try to do it kind of carefully. Be -9.5. It's going to work out. Okay. Then -19 twice, I get 0, 1, 2. So y equals 2 in agreement with what we know. Then, if I want to get row 1, 0 here, take row 1, minus 1.5 times row 2, give me 1, 0, 1, 0, 1, 2. So again, x equals 2, x equals 1, y equals 2. Okay, and just refresh your memory. Make sure you understand how to do this. Be able to do it with 3 equations and 3 unknowns too. Okay. Well, I'm gonna. You also need to know how to express the system as a matrix equation. It's been over a week since we did matrix multiplication, so maybe we ought to review that. Okay, this system is what? If I multiply 4, 6 by xy, multiply the row by the column, well, I get 4 first times first plus second times second. So my first row, first column is going to be 4x plus 6y. 3 -5 times xy gives me 3x minus 5y. And now since I've got 4x plus 6y in the first row, and I've got 16 in the first row here, and these matrices are equal, I get 4x plus 6y equals 16. And second row of this matrix has to equal the second row of this matrix, so I get 3x minus 5y equals -7. And that was my original system. Okay? That's one illustration of matrix multiplication. Another kind of problem you might see is I'll just use that matrix since it's there, but then I have B equals -1, 5, -4, -2, and C equals 2, 7, -9, 4. Then what does 2A plus 3B minus 5C equal? Okay, so if you give them three matrices, ask to calculate this, it's very easy. We just write it out. It means 2 times matrix 2, 2, 6, 3, -5, plus 3 times the matrix -1, 5, -4, -2, minus 5 times the matrix 2, 7, -9, 4. At 2, we're going to get 4, 12, 6, -10. And then we're going to get 3 times all these, -3, 15, -12, -6. Then plus a -5 times all these will give us -10, -35, 45, -20. Stand it out here. So that equals what? Well, first row, first column, plus first row, first column, plus first row, first column gives us 4 minus 3 minus 10. First row, second column numbers give us 12 plus 15 minus 35. And then we're going to get 6 minus 12 plus 45, and then -10, 6 minus 20. And then we add these up. That's going to give us -9. That's going to give us -8. If, check my arithmetic, this should give us 39. And this is going to give us -36. Okay. Then you might also be asked to calculate AB plus C. What's that equal? 2, 6, -3, -5, multiplied by -1, 5, -4, -2, plus 2, 7, -9, 4. Multiply first row by first column. I get -2 here and -24 here. That's -26. First row times second column, 10 minus 12 is -2. First row, first column, -3 and 20 is 17. First row, second column is 15 and 10, which is 25. I didn't go through all the details of multiplying the rows by the columns, but we've done it. And y'all have apparently done it correctly, but you did the homework. And what we get is negative 24, 5, 8, 29. If I did the arithmetic right throughout. So just reviewing, you should be able to do all these things. Okay? Okay, so there's a document that I'm going to email you this afternoon, so be checking your email. I think I might have posted a copy, but probably not. It's a PDF. And you got problems numbered 1 through 300, and it's selected problems. There might be 100 problems. Now, what I recommend you do is read it. I don't expect you to work 100 problems. But read it. Read each problem. Think about how you would solve it. Think it out and do it. Okay? Just get your first thought. How would I solve this? Mark the ones you're pretty unsure of, and go back and review those. Okay? And I'll give you some other stuff too. The test will be in the testing center on Monday. It's designed to be 2.5 hours, and often people take twice as long as they should. So I will probably break it into 2 parts. So that if you need to take it in 2 sittings, you can do that. Okay? Now it's really designed to be able to take both parts at once, but just take one at a time. Make sure you get it done before you ask for the other one. Okay? Your alternative is to take the test more or less in the time frame that it's designed for, give each one roughly an hour and a half. And you make that decision when you get there. I recommend that you don't get too hung up on any problem, because that's what ends up taking people twice as long. Get hung up on this thing though, do what you can here, go to another sheet and work something else. Work everything you can work quickly and then come back and fill in the blanks. Your subconscious will be working on those blanks while you work things that you know how to do. Okay, then you'll know, okay, I've got this much under my belt. Let's go back and pick up, pick the low-hanging fruit from what we've got left. Okay? Make sense? Okay, if you have questions, email me. Come by, I have office hours each day that we posted, no, email them. And be sure you spend time reviewing. Y'all have done a pretty good job of that throughout the course. I think y'all have done a good job with this course. Okay. Most of the class I'm seeing and some pretty good results and some pretty good work habits. Okay. So make sure you follow up, close it out with a good grade. I'll also say that I will accept final exams as late as a week from Monday at 5 o'clock. Exam week is officially over on Friday. So you have any time during that week, but I don't have to have grades in until Tuesday morning. So if you do happen to want to use next weekend, and I don't recommend that you do because you want to get on with your life, but it's an option. Okay. Okay. Any questions? Stick around and ask them, or email me, or whatever. Fair enough.